Okay, great. Well, glad to have everyone here with us today. We get to hear from Alessio D'Errico. I'm sorry for my
Perfect.
English pronunciation. Alessio got his undergraduate degree at the University of Naples. He then moved to work in the SLAM group, which was basically a spatial light modulator group under Lorenzo Marucci. Then he recently started his postdoc in the SQO group. I'm not actually sure what that means. What does that mean?
Structured Quantum Optics Group.
Okay. Awesome.
Recently, it's 5 years ago, but
okay. Not so recently moved to Ottawa to the structured quantum optics. So
By the way, there is a debate that is structural or structured.
I would say structured personally.
Structured.
Yeah. Okay, Alessio, turn the time over to you.
So thank you very much, Sean, for the introduction. So in this talk, I will actually kind of go through a set of experiments and works that we did in both Naples and Ottawa. Also in particular with Francesco that is online. So these works are about implementing this sort of platforms that are equivalent to realizing some quantum work process, but using structured light. And the idea is to use these platforms to somehow understand fundamental properties of the dynamics of particles in a lattice. By the way, I don't know if people can hear us or can hear me online. It's okay? Okay. So, as I was saying, these are works that I started working on this during my PhD, and then we are quite having many projects in this research line, especially in the last year. Yeah, so I started, as John was saying, I started my university and also PhD in Napoli, and this is actually my hometown that is 50 kilometers away and is very similar to Orange Country. Maybe some differences, like beaches are more rocky than sandy, right? And here I work with Lorenzo's group, in particular with Filippo, who did the first quantum work experiment, I think partially in Ottawa, partially in Napoli with you, Ibrahim.
Yeah.
And yes, during my PhD, there were a lot of research going on using quantum walks to simulate topological insulators. In particular, there was a strong collaboration with the group in ICFO led by Professor Levestein. Then, after my PhD, I moved to Ottawa. I started working on mostly other topics like photon characterization, quantum imaging, and also surviving the winter. This is Ottawa, literally. A few days ago, it was something like minus 15. I don't know how it's today, guys, but I'm glad I'm here for the moment.
Minus 15 in
the flat temperature. And yes, so, but then 1 year ago, Francesco joined the team, coming also from Napoli, despite I warned him about the weather, but he came anyway. And so we started working on some old ideas, some new ideas, for example.
Do you get a big wrench when you go to Ottawa?
Not really.
Oh, you. Okay. Welcome to Ottawa. Here's your wrench.
I tell you the story.
Okay.
And yeah, so actually also this summer, Mary joined us for a visiting, same group, and together with Nazanin and Lucas that is here, we also performed another experiment that is another way of performing quantum works with structured light in a fully reconfigurable way. So I will mention also this kind of platform that is a work in progress that we are going to publish hopefully very soon. Okay, so let's start from the basic. I don't know what the okay. So what is a quantum walk? A quantum walk was introduced as an analog of the classical random walk, but with some quantum properties. The basic idea is that while in the classical random walk, in the simplest case, you have a walker that tosses a coin and depending on the outcome, moves left or right. And that's the simplest case scenario, and you know that you can have some sort of diffusive behavior of the probability distribution of the worker. Now, things get completely different if you assume that the coin or the worker, or both, has some quantum properties, so they are quantum states. So the idea here is simulating the evolution of a particle with some internal degree of freedom in a lattice or a graph. More precisely, the starting point is, okay, we have this two-level system, which can be a particle with a spin or a photon, for the polarization of light. And the coin tossing operation should be equivalent to a transformation in the spin degree of freedom. So it's literally some sort of unitary operation that you apply on this internal state. Then you want to apply a transformation, a movement on the lattice that is conditioned by the internal state. And so you can implement a so-called shift operator. And the basic idea is that if your spin is up, you can move right. If your spin is down, you can move left. Of course, you can think also of other variations of these protocols, but essentially what matters is that at some point you have a movement in this lattice space that depends on your internal degree of freedom. And so the quantum world can be defined as just the repeated operation of these actions multiple times. And unless you don't introduce losses, this is also a unitary process, which means that you can see here a first main difference from comparing it with the classical random walk. And the idea is that it's a unitary process. The final state depends on the initial state. So essentially, while in the classical random walk, you have a Markovian process, you have no memory effects. In this case, the final probability distribution can be affected by your initial state. So you can start with spin up or a superposition of spin up and spin down, and you can have probability distributions that are, for example, either symmetric or asymmetric. This is an example of the evolution over in time. And you can see that the probability distribution is also a different shape from the classical random walk. In the classical random walk is a Gaussian that spreads diffusively. So the width of the Gaussian increases like with the square root of the time step. In this case, no, you see something that is peaked far away from the origin. And if you look at the standard deviation, it increases linearly with time. So we say that is a ballistic evolution. And this is a consequence of quantum interference, or if you like, of the coherence properties of this process. So you have different paths that can interfere destructively, tangentially in the origin, around the origin, and constructively on the edges. Now, in most of our experiment, we were interested in using this process as a way of simulating some effective Hamiltonian. So it's a unitary process. You can associate a Hamiltonian to it just using this formula. And the idea is that, okay, maybe this Hamiltonian is similar in some general sense, maybe the same symmetry, same topological structure, or same eigenvalues of, with respect to the Hamiltonian of some system of interest. So the main idea is using these quantum world platforms to simulate the dynamics of a particle in a crystal. Okay, and there are many different ways of implementing these quantum world processes. People have done it in, let's say, trapped atoms or trapped ions in superconductive system, but probably the most popular implementations are the ones with light. Very simple because you can use the polarization as the analog of the spin, so as the coin degree of freedom. And then you can choose any high-dimensional degree of freedom of light to implement the Walker space, so the lattice space. You can choose the path, you can choose the time being, you can choose the frequency, or even the orbital angular momentum. In all these situations, you need to find some optical devices that couple the polarization degree of freedom and this higher dimensional degree of freedom. For example, you can think of a calcite crystal that deflects light in different paths depending on what is your linear polarization. All these implementations have different advantages and disadvantages. Some are not fully scalable, some can be not so versatile. So to implement different operations, you might have to rebuild another setup with some variations. Some might be limited to one-dimensional implementations and not two-dimensional and so on. In our approach is based on using, again, polarization, but also the wavefront of light, or if you like, some degree of freedom associated with the wavefront curvature of a single light beam. So the basic idea is that you have this set of optical elements, and the way they transform polarization and phase of a light beam is equivalent mathematically to quantum walk. So now I will go through a series of strategies to implement this sort of operations that we developed over the years. And then in the second part of the talk, I will show you at least a few implementation or applications of these protocols. So let's start. What is the basic idea? We need to find an optical device that changes the structure of the wavefront of light depending on what is the polarization state. So let's say if you have left circular polarization, you do something on the wavefront. If you have right circular, you do something else. Originally, we were doing this using the orbital angular momentum degree of freedom, but in that case, we were limited to one-dimensional lattices. So we later generalized, this was done during my PhD, the idea to a simpler degree of freedom, that is the transverse component of the wave vector of light. Now, to understand how it works, let's start with a simple optical element, which just only changes the polarization of light. And this is the alpha wavelet. I don't know how many of you are familiar with this optical element, but this is just an anisotropic element that can be used to rotate the direction of oscillation of linear polarization just by rotating this wavelet in the transverse position. And it can also be used to flip the handedness of circular polarization. And this is independent on the orientation of the wavelet. So if you have left circular, you go to right circular. If you have right circular, you go to left circular. Moreover, it also adds a global phase that has a sign that depends on the input polarization, and is also given by the orientation of this element in space. So you rotate this element, you add a different global phase. Now, if it's a global phase, normally we don't care much about its effects. But what we can do, we can make this phase alpha spatially dependent. Imagine that you can do it with some particular technology. So in this case, what will happen is that depending on the input helicity of the polarization, you will distort the wavefront of light with one phase or the opposite one. It can be even simpler than this. We can just apply a phase alpha that is a linear function of one of the Cartesian coordinates. So let's say alpha is a linear function of the x direction. In this case, what happens? If you have less circular polarization, you are introducing or increasing the transverse component of the wave vector of light along the x direction. So you are literally introducing a wavefront tilt. If you go with right circular polarization, you introduce a tilt in the opposite direction. So you decrease the transverse component of the wave vector. Essentially, if you look at this device between cross polarizers, it looks like a diffraction grating. So if you look at the far field, depending on the circular polarization, it will deflect your light beam left or in the, let's say, left or the right direction. And this is not necessarily an half wavelet. It can be any other kind of optical retarder. And the idea is that we fabricate these elements in our labs, both in Ottawa and in Napoli, actually, using liquid crystal materials, liquid crystal devices. And the nice thing of liquid crystals is that if you just apply an electric voltage to them, you can modify the optical retardation. Modifying the optical retardation means that this object can in general implement this transformation. Okay. So the action on the polarization of light is a superposition of the identity operator, so nothing happens, plus this shift operator, which is the one that we were looking for the standard quantum walk. So if you go left, you become right, and you add a transverse wavefront distortion. And this depends on this delta parameter that we can calibrate just with an electric voltage. So if you want to understand the action of this device in the lab, just imagine to shine a large light beam on the G-plate and then look at the far field, so you can look at the focus, at the focal plane of a lens. If delta is equal to 0, you only see a spot in the center. If it's equal to pi, you will see two separate spots with opposite circular polarization. But you can also introduce intermediate values of delta where you can also have a spot in the middle. So essentially, the far field of the G-plate is equivalent to the lattice space that we want to populate with our quantum work dynamics. And how do we implement the quantum work? We simply stack on top of each other many of these optical elements, for example, alternating G-plates and waveplates, uniform waveplates that they play the role of the coin tossing operation. And so this is the basic idea, but
do you go to the Fourier transform for each one of those? Do you put each successive plate in the Fourier transform, or what?
No, we all stack them together, and then we do the Fourier transform,
I
and we
see.
see
So
what
after-
happens in
at
the
the end.
lattice.
Okay.
The funny thing of this system is that since you can turn delta on and off, the G-plates on and off, you can have all of them together and see what happens for 1 step, 2 steps, 3 steps, and so on and so on.
I guess
So you
since
have-
it's just tilt, then you don't need to worry about going.
Yes,
yeah,
yes,
okay,
yes.
okay.
And the other advantage is that since you can tune this parameter, you can look at different protocols, not only one. For example, you are introducing the possibility that between one step and the other, there is some probability that the worker stays in his original position. And this is important because it allows to actually look at different topological phases of these protocols.
It also assumes that your Rayleigh length is much, much longer than your space.
That's a very important thing.
Yeah.
It was a limit of the setup. So I'll
Mm.
tell you now how we surpass this. So we are doing some sort of paraxial approximation. So actually the periodicity of this diffraction gratings is very large. This lambda was something like 5 millimeters. And so you have to shine it with very large beams. This was originally some sort of limit, but actually we recently surpassed this, making all the device very compact. So I'll show you how this is done. And just another thing about this implementation is, okay, you can have a G-plate patterned along the X direction, but you can also do it along the Y direction, just rotate it. And this allows you to implement quantum works in two-dimensional lattices, let's say square lattices or triangular lattices. And for example, an example of a protocol is two G-plates in orthogonal directions and also a waveplate to implement some coin operation. You can think of variations adding more waveplates in the middle or different retardations. This was particularly nice because we found out that it implements a quantum Mole insulator. So it's a system where you can have this sort of quantum Mole effect. And so, okay, this is actually, as John was saying, how the device looks like in the lab. So it's a set of wavelets that we try to stack as close as possible to each other to reduce diffraction effects. Another thing you could do is just image with a 4F system each wavelet into each other. Of course, it becomes more bulky and more long. So the fundamental limit is just that you want your transverse wave vector components to be much smaller than the longitudinal component. So you can do something like hundreds of steps, but at some point you start reaching a regime that is non-paraxial. Okay, and this is how the probability distributions of a two-dimensional quantum work looks like in the focal plane of the lens that is placed after the system. Now, this was our original approach. So it was like, okay, we have these devices, and let's find different ways of arranging them, and let's see what kind of protocol or unitary operations they are implementing. Then actually, after I left the group, Francesco and Filippo started working on, I would say, a top-down approach, which is I have a unitary operator or an Hamiltonian, and I want to implement it with my optical devices. So how do I do this? To understand, we need to look at the mathematics of these unitary operations. Essentially, they are processes on a lattice. So you have a discrete translational symmetry. So if you have some background in solid-state physics, you may remember the Bloch theorem, which just says that you can diagonalize, at least partially, this Hamiltonian or this unitary in terms of these so-called quasi-momentum eigenstates. They are literally just the discrete Fourier transforms of the position eigenstates on the lattice. And in this case, the unitary doesn't matter what is the specific protocol, you just need the translational symmetry. Is this expression. So Q is a variable that is continuous but bounded in a so-called Brillouin zone. And essentially, for example, in one dimension, I say that goes from minus pi to pi in units of the lattice spacing. So I'm putting many units, many physical units to equal to 1. And this matrix is the important part. This is a unitary matrix that acts only on the polarization degree of freedom. So it's a 2x2 matrix, but it's a function of this continuous variable. How can we implement this optically? Our approach has the disadvantage that you can have a direct access to the quasi-momentum space. And it's very simple. Since the lattice is is here in the far field of a lens, the quasi-momentum space corresponds to the reciprocal lattice. So it's actually existing exactly where you place these wavelets. Essentially, the Q corresponds to the transverse position variable in this plane. And so this means that we need to find a way to just implement spatially varying unitary operations on the polarization space. And how do we do this? First of all, we need to know how to implement an arbitrary unitary in the polarization space. And this is easy. You just need 3 wavelets, 2/4 wavelets and 1/2 wavelet. And then you need 3 angles, alpha, beta, and gamma. These are equivalent to the Euler angles for rotations, both in quantum and classical mechanics. So essentially, by tweaking these angles, you can implement different kind of unitary operations, arbitrary ones. And so all we need to do is making these angles spatially dependent, so functions of this Q parameter, or if you like, of the transverse position. And so we need to prepare patterned wavelets where alpha, beta, and gamma somehow implement the unitary of interest. So it's a matter, in this case, of solving a set of equations that can give you the right values of these angles for each transverse position that implement your desired transformation. And this can be done relatively easily, and we can fabricate these wavelets in our lab so we can draw arbitrary patterns. So we have all the tools for implementing these transformations. Now, at this point, there is a small limit. So we solved the problem of compactifying the setup because you only need 3 wavelets for arbitrary number of steps. So there is no diffraction within the setup, within the 3 plates block, and so this is pretty nice. But these devices are fixed. So you have one unitary for a fixed number of steps, and you can draw the devices only for that particular situation. If you want to simulate not another unitary, but also another number of steps, you need to calculate and fabricate a new set of devices. So this is kind of a limit. In principle, it would be nice to be able to control with a computer the values of alpha, beta, and gamma point by point. Fortunately, we don't have such a technology, but we can do something similar by slightly changing our approach. And this is what we did this summer with Nazanin, Lucas, and Mary, which was basically, instead of having a variable alpha, beta, and gamma, we fix them, they are uniform, and we change point by point the optical retardation. And what is a device that does this action? Is actually, we don't have to fabricate it anymore. It's something that you can buy if you have $15,000 per device. But it's simply an SLM. It's a spatial line modulator based on liquid crystals. And so you can have 3 SLMs where the intermediate one is oriented at 45 degrees with respect to the other 2. In this way, you can implement also polarization transformations. And one can see, if you do the mathematics, you can see that this allows you, again, to implement arbitrary unitary processes. And so this was the last kind of platform that we realized to play around with this process and to investigate this lattice dynamics. If there are any questions, otherwise I will switch to the application part, also online maybe. All good?
It is 15 grand plus tax.
Per device.
Per device.
One of the reasons I joined Ibrahim's group is that when I had the interview, it was like, I have 16 SLM. I was like, wow, I have 3. Okay, so what can we do with this photonic analog processors? there's many things that can be done. Many people have studied, for example, the interplay between the classical and random walks, depending on what happens if you introduce the coherence. And so you can see the transition between these two regimes. In our case, we mostly try to use, as I mentioned, these devices as a way to investigate fundamental solid-state physics in the single particle regime. And there's many things that can be found out in these regimes, because, for example, there is a lot of investigation in the recent years on topological materials. And I'll give you an example of what this means and how topology and geometry play an important role in the physics of particles in a lattice. Okay, so let me go with an example that is actually a set of papers that are quite spread out over time. I will just mention results that go from my second paper in my PhD, an intermediate paper during my postdoc, and one that we just published last year. All these three papers, plus many other things, actually can be condensed in a few words. And so what is the idea here? Is trying to measure geometrical or topological properties associated with the energy spectrum of a solid-state material by looking at the probability distribution of a particle in a lattice. And so what are these topological and geometrical properties? Let's go back to our spatially dependent unitary. This is a 2x2 matrix, so we can decompose it in Pauli matrices, and the eigenvalues can be interpreted as some sort of energy bands associated with the system. This is why we have this analog situation with this similarity with solid-state materials. And the eigenvalues are also, the eigenstates are also dependent on this Q parameter. Now, one thing that I probably didn't mention is that this Q is periodic. So the values at minus pi and pi, or let's say at the edges of the Brillouin zone, are equivalent. So and this is important because sometimes it's bounding our manifold space, and so it allows us to define topological invariants. If we still focus on the local properties of this spectra, one can look at, for example, how to define, let's say, the distance between two eigenstates. So essentially, you have this manifold of quantum states, and you want to somehow introduce some sort of metric. And indeed, this can be done by introducing this quantity that is called the quantum geometric tensor. It contains essentially the derivatives of the eigenstates along the reciprocal space or the eigenstates themselves. So somehow it's telling us how eigenstates are changing in this manifold. And indeed, it can be shown that if you take the real part of this quantity, this is associated, is a good metric. So it gives a Riemannian structure to the manifold of quantum states. If you take the imaginary part, this is associated with the Berry curvature, which is probably a more famous object that is very important for particle dynamics. Actually, in recent years, the quantum geometric tensor has become more really interesting because people have shown that, for example, it's responsible for low-order corrections of non-adiabatic effects in particle dynamics. It has a singular behavior in correspondence of quantum phase transitions. And also, I will show you another example of how this quantum geometric tensor directly affect the probability of a quantum worker in a particular one-dimensional lattice. Now, this quantum geometric tensor describes local properties, so features that are can be explored in a few single points of the reciprocal lattice. But we can also look at global properties, or if you like, topological features. And there are many ways of introducing this. Essentially, I will focus only on the case that is one-dimensional, that is the simplest one. And in this case, if you want to look at some topological invariant, you need also symmetries, some symmetry protection. In particular, it's very nice to look at the chiral or sublattice symmetry. It basically means that your eigenstates are bounded, are confined in a plane of the Bloch sphere. So you can see them that are always living in this equatorial plane. In this case, there are few things that can happen. If you start changing the Q parameter. So if you start exploring how these eigenstates are changing along the Brillouin zone, sorry, to this thing, otherwise. Okay, in this case here, you can see that the eigenstates will start rotating in some direction and then going back. Notice that when you explore the Brillouin zone, you have to always go back to the original eigenstate because it's a periodic, yes, this periodic boundary condition, so it's a bounded system. Another possibility is that they start spanning the equatorial plane and continue filling it one time or two times. So you can start rotating around the origin multiple times. And this number of rotations is a topological invariant. It's called the winding number. And it's an object, it's some sort of ordered parameter that you cannot change by smoothly modifying your Hamiltonian, assuming that you don't lose the symmetry, the chiral symmetry. Interestingly enough, this quantity can also be expressed mathematically as the integral of the square root of the quantum metric. In this case, this is just a scalar because it's a one-dimensional system. And more intuitively, if you just a direct calculation can show you that this square root is nothing else than the derivative of the azimuthal angle that is spanned by this eigenvector. So you're just integrating this azimuthal angle over the Brillouin zone. Okay, so the question is, can we look at the probability distribution of a particle over time and understand what is the topology or the geometry of the system? The answer is yes. If we, and for that I need to introduce these so-called chiral eigenstates. They are just quantum states, coin quantum states that are perpendicular in the Bloch sphere, so not orthogonal to the eigenstate. So it's either this V of gamma or the minus V of gamma. The idea is that we can do projective measurements or looking at the projection on any arbitrary coin states. It's simply just a set of wavelets and polarizers. And so a quantity and observable that we studied a lot was this so-called mean chiral displacement. It's defined by this expression. So it's the mean value of the position after applying this gamma operator that is nothing else than the difference between the projectors on the two chiral eigenstates. Now, I'm not going to try to give you a physical intuition of this quantity. What matters is that we can easily measure it and it gives us the right information. The idea is that we consider initial states at t equal to 0 that are wave packets. So you can consider the Gaussian-like distributions in the reciprocal lattice with a uniform polarization or a uniform coin degree of freedom. And if you just do some simple calculations, a nice advanced quantum mechanics exercise, you will find out this result. You will find out that this mean chiral displacement is equal to the sum of two contributions. The second one is an amplitude that decays over time, so asymptotically goes to 0. This f of t is a function that oscillates around 0, so you can also take time averages and remove this contribution. And so you can isolate this first part that is nothing else than the convolution between the wave packet distribution of the initial quantum state and the quantum metric. Now there are two things that we can do. In our quantum works, we can easily implement arbitrary wave packets shapes because it just depends on the width of the optical beam that you're shining on the wavelets. So essentially, very simply, you can have a beam with a large waist, larger than the typical periodicity of the gibbets that you use, and this is equivalent to a localized state. Or you can have a narrow beam with a narrow waist, and this is a more spread out in the lattice space. It's just the typical properties of Fourier transforms. Okay, so let's look at the localized state. In the case of a localized state, this wave packet is basically uniform in the reciprocal lattice. And so what we are looking at is the integral of the square root of the quantum metric. I showed you before that this is nothing else than the winding number, the topological invariant of the system. In other words, the mean chiral displacement can be used to measure, just by looking at bulk properties, the probability distribution of, to measure the topological invariant of the system. And in our experiment, since we could tune this delta parameter, we could actually explore the mean Carrel displacement for different topological phases. So with winding numbers 0, 1, and 2. Interestingly enough, you can also imagine to have some process where at some point you change the winding number of your process. So in time, you change Hamiltonian. And the mean Carrel displacement is also able to follow the change in topological invariant. So it will switch from winding number 2 to 1 if you change, to a mean value of 2 to 1 if you change the winding number of the system. Instead, you can look at more delocalized wave packets. So if it's something that is narrow enough in the Brillouin zone, you will extract a quantity that is essentially the quantum metric in that position of the reciprocal lattice that you are analyzing. If you want to have a more physical or intuitive understanding of this metric, this is just this infinitesimal area that is subtended by these three vectors, P of gamma, N of Q, and the eigenstate at a slightly different position in the quasi-momentum space. And so we tested this result for first numerical for different solid-state physics models. So it doesn't work only for quantum walks. We checked it for the polyacetylene chain, that is the standard model of topological insulator, and also for graphene, which also exhibits chiral symmetry, but is not a topological system. And also in this case, you can analyze you can look at the mean Carrel displacement and extract the quantum geometric tensor. And we also did an experiment last year together with Nazanin and Francesco, where for our quantum protocol, we reconstructed the quantum geometric tensor that, as you can see, if you span the reciprocal lattice, averages on the topological invariant of the system, which in this case was equal to 1. And yeah, so this was one of the many examples of the things you can do. I will just fast forward on some other applications now. I don't know if I've done.
So just to emphasize, the mean Carrel displacement is extremely important because when we create a quantum system, let's say a quantum simulator, some people criticize and say that, is that doing the right things or not? And in order to, let's say, address these questions, if the dimensionality is increasing, the number of measurements if you want to do the tomographic protocol, it requires exponential measurements. But with this kind of mean Carrel displacement, essentially you can just give the result and telling you that, well, this is the right machine or is the wrong machine. So it's extremely useful. I would say the single shot measurement essentially for this device that will provide you that information.
Yeah, it's true. In practice, every time we try a new platform, we say, okay, let's check the mean Carrel displacement of this system, because if there is some small misalignment that breaks the chiral symmetry, you will not see anymore the behavior that you were expecting. And moreover, actually, it has been used in many other platforms, new platforms to benchmark. I think one of the most interesting ones was the first demonstration of a new phase of matter that is the so-called topological Anderson insulator. Is something that uses both disorder and topological features of systems.
Just to clarify,
yes.
Is that a theorem or a heuristic? That the mean Carrel displacement will tell you. Is there a theorem?
Yes.
Or,
yeah.
Okay.
Yeah.
Yes. So we have the calculations that demonstrate that you can converge to either the local or global features of the system. Yes. And well, there's many other things you can do. For example, since we have access to wave packets, we can also understand what is the energy band structure of our system, because if you prepare them in the right polarization, you can also look at the group velocity of them, and this is given by the derivative of the energy bands. This is one of the possible applications or ways of benchmarking our platforms. You can actually do something quite surprising, in my opinion, that is also simulate external fields. So imagine that you want to simulate a particle in a lattice with an applied external electric field. You can do it in a very nice way that is just at every step, you can laterally shift your giblet by an amount that is proportional to the time step and to the strength of the field that you want to apply. And the idea is that basically you are just shifting the reciprocal lattice, because this is what you are doing to the magneto for a constant force, external field. And this was useful because we could test some very known processes, for example, Bloch oscillations and Landau Zener transitions, that are processes in which you can observe the refocusing of the quantum state on itself. And in one case, it's an adiabatic effect. In the other case, it's a strongly non-adiabatic effect that concerns a double passing through a singular point in the spectrum. And this was useful also for the two-dimensional quantum walk, where we could observe the effect of an external. So we could observe the effect of an external field on a wave packet. And there is some funny effect that happens here, that the Berry curvature of the system plays the role on an effective magnetic field, and so it can deflect the wave packet like a null effect in the direction perpendicular to the direction of the applied external force. And this is a way that you can use for measuring the topological invariant of this system, that is called the Chern number. It's given by the integral of this Berry curvature, and this some sort of higher dimensional winding number. So this is another thing that we did at the time. So we prepare many wave packets and look at the average anomalous displacement. And from the slope of this displacement over time, we could understand what was the topological invariant of the system. And these are some old applications. Now we are working on a bunch of other possible projects. So we are using these platforms for benchmarking new ways of doing quantum process tomography. So, for example, we recently published this approach that is called Fourier quantum process tomography, which requires only 7 spatially resolved measurements instead of the traditional 16. Another work that actually we posted on arXiv 2 days ago is about using these platforms to engineer the interaction of a qubit with an environment. For us, the qubit is the polarization, the environment is the lattice system. And we can literally find the wavelet patterns that implement the set of cross operators that you want. And this can be used also for studying some fundamental features of the interplay between qubit environment interaction, geometric phases, and topology. And actually, I want to go back on this sort of work we did the past years, because I personally didn't fully understand it, and I think there is something more written in that, but we can talk about that in question of time. Right now, we are working on using this platform for implementing quantum walks in lattices with some periodic boundary conditions, at least in one direction. So you can think of a cycle like a benzene molecule, or a torus, or a cylinder. And there is a very neat trick for just doing this with the same identical setup. And of course, a quantum walk is not fully quantum if you don't use single photons. And so we are going to use some camera technologies that can allow us to look at spatially resolved coincidences. And so our plan is to feed this quantum walk setup with photons that are correlated in positions or anti-correlated in momentum, and see how the spatial correlations are affected by the quantum walk dynamics. Actually, some works that
this is done. It will be
one of these.
hopefully will be
a version of this
tomorrow on arXiv. Yeah.
Yeah, that's it. Thank you very much for being here and for listening to my talk. Thank you.
Questions?
I have a hand on Zoom.
Is Kai
Oh, Kai.
Is he clapping or?
clapping or question?
Oh, Kai, are you clapping or are you raising your hand?
It was more like
Just clapping.
So I have a question for you. So basically this all relies on coherent.
exactly.
Have you explored partially coherent or decoherent systems or incoherent systems?
The coherence, not really, but it could be done in principle. You can just feed the system with, I don't know, a lamp or an incoherent laser. There are many experiments that have seen that, for example, if you introduce a decoherence, in our case, an effective decoherence could be stacking too many of these plates at a longer distance. And so what happens is that you start having some lateral position dependent effects And so when we were doing the simulations at the time, we wanted to avoid this actually. So we didn't do the experiment for this. And you can see that in that case, you have additional effects due to the propagation of the beam in the setup that give you some sort of Gaussian-like probability distribution.
Yeah, I was just wondering, does it give you the classical result? It just gives you the,
Yes, it gives you something like Gaussian. So it has been shown actually this first experiment with cassette crystals. Let's figure it out. Okay, that's all. But there was this experiment where they were using a set of cassette crystals, and just by misaligning some of them, they were reducing the probability of interference between different paths, introducing them with decoherence, and then losing interference effect. And so you could see the transitioning from ballistic to Gaussian probability distributions. There's another thing that can be done that is, and we do sometimes, is simulating disorder. In our case, we simulate a so-called temporal disorder. So you assume that between one step and the other, there is a deviation in the parameters of your protocol. For example, the delta parameter can be slightly different. And this can lead to effects that, for example, we have some experiments that we have done with Mary that are related to seeing a transition from ballistic to super diffusive to diffusive dynamics if you average over many of these events. So even that is some sort of difference process.
yeah, that makes sense. Other questions? All right, let's thank Alessio then.